we say that xt and x of j omega, they form a Fourier transform pair. Okay, and if when we have to sketch this x of j omega, it is a function of omega, and generally it is a complex valued function. Okay, so when we have to sketch this x of j omega, since it is a complex valued function, we can write it as magnitude of that function and phase of that function. Okay, and if you sketch this x of j omega as a function of omega, that is called the spectrum of the signal. And if it is a complex, sometimes it is a complex valued function of omega. So then we have to sketch the magnitude and phase separately. So if we sketch this magnitude of this as a function of omega, it is called the magnitude spectrum. And if we sketch the phase of that function as a function of omega, then it is called the phase spectrum. Then it is called the phase spectrum of that signal xt. So let us consider this signal e to the power minus at, and assuming that a greater than 0. Can you tell me what is the Fourier transform of this signal? X of j omega, this is the definition, integral minus infinity to infinity xt e to the power minus j omega t dt. Now if you substitute xt with this, then you will get this integral 0 to infinity e to the power minus at e to the power minus j omega t dt. And if you simplify this, we will get this integral e to the power minus a plus j omega t dt. And if you do this integral, you will get 1 upon a plus j omega. This is the, if you do this integration, you will get this. Okay, so this is the Fourier transform of the signal or the spectrum of the signal. Now, if you want to sketch the spectrum of the signal, this is a complex valued function of omega. So we have to sketch the magnitude and phase separately. So what will be the shape of the magnitude spectrum? What is that? X of j omega is what? Is it 1 upon a square root of a square plus omega square? That is the magnitude. So if you sketch that, it is something like this. Okay, this is the shape of that function. And what about the phase? This is called the magnitude spectrum. Now, what about the phase spectrum? What is the expression for the that phase? X of j omega, is it minus tan inverse omega by a? Is it the phase of that function x of j omega? Is it this? Minus tan inverse omega by a?
Yes, sir.
So what will be the shape of that if you sketch that? X of j omega. I am sketching the phase angle. What is the value at omega is equal to 0? Is it 0? And what happens when omega tends to infinity? This function tends to what?
Pi by 2.
Is it pi by 2? And there is a minus sign here. So it is something like this. This is minus pi by 2. And for the negative values of omega, this is something like, as omega tends to minus infinity, it is pi by 2. And as omega tends to infinity, it is minus pi by 2. That minus is because of this minus. And now let us consider another example. If you are considering a signal, let's say the Fourier transform of the signal, We are considering some signal xt, and we are given the information that the Fourier transform of the signal is something like this. It is a rectangular pulse. Okay, let me denote it by 0 and w minus w1. And what is this expression in terms of rectangular rect function? We are saying that x of j omega is what? Rect omega by 2w. Is it that? Rectangular function having width 2w. Okay. Now let us try finding the Fourier, the signal corresponding to this Fourier transform x of j omega. How to find x of t? What is the inverse Fourier integral? Inverse Fourier integral is xt is 1 upon 2 pi integral minus infinity to infinity x of j omega e to the power j omega t d omega. This is the inverse Fourier integral. And if you use this function for x of j omega, we will get this expression integral minus w to w, and its value is 1, and e to the power j omega t d omega. And if we do this integration, we will get e to the power j omega t by jt minus w to w. This is sine wt by pi t. Can you find this expression in the sinc form? This is the corresponding signal xt. Can you find the signal as a sinc function? Please try that.
Is omega by pi. Sync omega
xt
t by pi.
xt is omega by pi.
Sync omega t by pi.
Sinc omega t by pi. Sorry, it is not omega, it is wt by pi. This is w. Okay.
Yeah.
Omega is another function in the frequency domain. This is w. That is used to denote the width of that pulse. Okay. So now let us try sketching this Fourier transform pairs. We started with a rectangular pulse of width t1.
Sir, here isn't it omega? Because we
What
drew
omega?
the graph
What?
for omega. Sir, in the above part.
No, this one I am considering a rectangular pulse in the frequency domain. I am assuming that the Fourier transform of a signal is a rectangular pulse. Now I am trying to find the corresponding signal in the time domain. Are you getting that?
Sir, so here the W thing is the width in
W,
omega region.
yeah,
So,
yeah. W is the width in omega. So the integration is with respect to omega. This is e to the power j omega t d omega. Inverse Fourier transform, that integration is with respect to omega for finding the time domain signal xt.
yes, sir. So, will it be a function of omega also? Like final XD?
How xt can be a function of omega, because you're integrating with respect to omega, then how it is a function of t only. This is from minus infinity to infinity integrating with respect to omega, so it cannot be a function of omega. It
Okay,
is a
sir.
function of t.
Okay.
It is a function of t because integrating with respect to omega, and there is a value constant t here because t is constant with respect to this integration omega. So this will be a function of t.
Okay, sir.
Okay. So now this is the expression for this is the signal xt if you do that integration. And if you convert it, when you convert it into the sinc form, the standard form, then you will get it as w by p. It is not omega. W by pi. This is the width. W by pi. Sinc wt by pi. Okay. So now let us sketch those functions. We started with a signal that